Hello and welcome to our very important discussion for today. And our objective will be we have two objectives. We will talk today, our first objective will be the discussion and the learning of the origins of macrophages in our body. And we will learn that macrophages have different functional capacities. They perform different functions and they are located structurally in different places. However, there are two origins of macrophages in our body. Depending on where are these macrophages located. We talked in the past that we have macrophages that are sentinel and resident macrophages that detect and initiate the inflammatory process. So these resident macrophages, these sentinel resident detecting macrophages, they detect invaders, detect microbes, detect the necrotic debris of cells that are damaged through trauma or ultraviolet radiation or physical agents or chemical agents and so on and so forth. These are resident localized macrophages, like the Kupffer cells in the liver, like the alveolar macrophages in the lung, like the sinus histocytes in the lymph nodes and the spleen. And there's also the microglia, which are the macrophages of the central nervous system. These are resident stationary macrophages that detect the onset of the inflammation, and they send cytokines to recruit other macrophages from the blood circulation. Now, these are the second type of macrophages we will talk about. We talked about the resident macrophages, and now there are the circulatory macrophages. These circulatory macrophages, they originate from a different, their origin, their synthesis comes from a different location. And the resident macrophages synthesis comes also from a different location. The resident macrophages come from the embryonic yolk sac and the liver in the embryonic development, while the circulatory and the circulating macrophages in the blood, these inactive macrophages that become activated once they detect the cytokines being released by these stationary macrophages to recruit, the circulatory macrophages. They are actually called monocytes. They are undifferentiated. But once there is an inflammation, the receptors on these circulatory monocytes, they detect these cytokines and then they become activated and they differentiate and proliferate into mature macrophages. This is the second class of macrophages. These are called the monocytes, and they don't originate from the embryonic yolk sac and the liver in embryonic development. But these monocytes, these circulatory monocytes, they originate from the bone marrow. They originate from hematopoietic stem cells that come from the bone marrow. So that's what we will talk about today. That's the first objective. And the second objective is, we know that macrophages have three distinct functions. The first function is, once there is inflammation, these macrophages, they are able to detect cytokines being released from the sentinel and the resident macrophages, namely the Kupffer cells in the liver, if there is an inflammation in the liver, or macroglia if there is inflammation in the central nervous system, sinus histocytes if there is inflammation in the spleen or the lymph nodes, and alveolar macrophages if there is some sort of inflammation in the respiratory system, in the lungs. Once these sentinel cells secrete their cytokines, now macrophages' first function is to detect these cytokines released from these macrophages, and themselves they secrete further cytokines to recruit more macrophages. So the first function of the macrophages is send cytokines to recruit more macrophages from the blood, and these cytokines that are detected by the macrophages, they activate the macrophage and cause the macrophage itself to release more cytokines in a positive feedback manner to recruit more macrophages. And the more macrophages come themselves, they secrete other cytokines, and it's an ongoing process of recruitment, like a domino effect. So each macrophage becomes activated after binding a cytokine that was released from a previously activated macrophage, and then the macrophage would send other cytokines to activate an inactive circulatory monocyte, and that inactive circulatory monocyte would become activated and secrete other cytokines to recruit more and more. And this is the element that causes chronic inflammation, because we keep on having these macrophages recruiting more macrophages to come and destroy tissues and engulf and cause so much necrotic debris. So that's the first role of the macrophages: detect cytokines and recruit. Detect cytokines, become activated, and recruit other macrophages by secreting cytokines. The second role that these macrophages play is the macrophages would come and become activated, and they would actually, once they are activated and once they recruit other macrophages, the second role is they start engulfing and endocytosing necrotic debris and microbial products and microbial agents, like these harmful stimuli like viruses, bacteria, and parasites and fungi, and it will engulf them. And we talked in the past about how a lysosomal vesicle will fuse with the phagocyte, and then we would have a phagolysosome where the lysosomal enzymes would use reactive oxidative species and nitric oxide species to destroy and disintegrate all of these ingested microbes by the macrophage. So they have microbicidal activity. So the second role of the macrophages is microbicidal activity. And the third role of the macrophage is to pave the path and the way for healing and repair. So they don't only damage, they also build. So now we have to understand, how does the macrophage know what to do? How does the macrophage know which of the three functions to perform? Should the macrophage perform function number one, which is secreting cytokines to further activate other macrophages, and these other macrophages, they will send cytokines to other macrophages, and the accumulation and recruitment of more macrophages? This is the first role. Or should the macrophage do the second role, the microbicidal activity, the destructive activity of engulfing all the necrotic debris and swallowing, engulfing all the microbes and necrotic debris and all of these damaging structural accumulations? That's the second role. Or should the macrophage now begin the process of healing and rebuilding and remodeling? So how does the macrophage know which of the three roles? We talked about the origin. Now we will talk about how, and it depends on the cytokines. So there is a cytokine that once binds to the receptors of the macrophage will cause it to do function number one, secrete cytokines like a dominoes effect to bring in more macrophages to the site of inflammation. Or action number two, there's different cytokines that cause the macrophage to perform microbicidal destructive activity of engulfing all the necrotic debris and combating and engulfing microbes. And there is different cytokines that once bind to the macrophage cause the macrophage to begin the healing process and the rebuilding process. So it's the same macrophage, but it is the cytokine that binds to its respective receptor, and once it binds to that particular receptor, the macrophage will do the function. It is the signal, the cytokine that dictates the macrophage to perform the particular function. So each function has its own cytokine. And you will not have different cytokines that lead different functions bind to the macrophage at once. It doesn't happen that way. It's only at different stages. In the beginning, the interleukins and the cytokines that recruit the macrophages are sent first. Once that phase is over, we will have cytokines that begin the microbicidal activity. And in the end, we will have cytokines that begin the healing and remodeling process. What are these cytokines? We will see them now. Maybe you don't need to know them in detail. Maybe you will not be asked on the exam in pathology or in the USMLE, what is that particular cytokine that causes function number 1? What is the particular cytokine to cause number 2? What is the particular cytokine to cause number 3? Maybe if you are into the research of pathology, you need to know them. But it does not harm to just know what they are. Maybe you are required to know them for the USMLE. I doubt it, but if you're not, just familiarize yourself with them. Okay, so now let's begin. So what do we have here? We have the first, this is the origin. These two diagrams describe for us the origin of these macrophages. The first origin will give us a macrophage in 4 steps. And that is when in acute inflammation, we have resident sentinel macrophages, like the microglia in the central nervous system, like the sinus histocytes in the lymph nodes and the spleen, like the alveolar macrophages in the respiratory system, and the Kupffer cells in the liver. They send cytokines that go in the blood and recruit these monocytes. Where these monocytes come from? They come from the bone marrow. The bone marrow will give us hematopoietic stem cells. Step number 1, the bone marrow will stimulate the synthesis of hematopoietic stem cells. Hematopoietic stem cells, step number 2 would differentiate into monocytes, and these monocytes will circulate in the blood. And this is step number 3. Step number 4, once the resident sentinel macrophages in the onset of inflammation, when these resident macrophages, their receptors bind, we talked about the different receptors that these resident sentinels macrophages have. They have the toll-like receptors, they have phagocytic receptors, they have different receptors that bind necrotic debris, that bind viruses, they bind lipopolysaccharides and carbohydrates and proteins or glycoproteins that are unique to these microorganisms, these invading viruses, bacteria, fungi, and parasites. And once they detect them, these macrophages, when they bind to them mechanically, they start sending these cytokines, and the cytokines would actually cause the recruitment of these monocytes. And these monocytes, once they differentiate, they secrete more cytokines to recruit, to cause the bone marrow to just go through this leukopenia and secrete more and more monocytes. So the first step, the bone marrow, will give us the second step, hematopoietic stem cells. Hematopoietic stem cells will give us the monocytes circulating in the blood. The blood monocytes will now be activated by cytokines released by the microglia, by all these alveolar macrophages, the Kupffer cells, and the sinus histocytes. They will become activated macrophages in inflammation, and they will be activated. So now you know where the source of the first form of the first form of macrophages, these combating macrophages that circulate in the blood. They are undifferentiated. They become differentiated once there are this proper cytokines released during inflammation that lead them to be activated, to lead them to be marginalized. They start to get closer to the site of inflammation. And you know, the cytokines, they are not only detected by inflammatory cytokines, are not only detected by monocytes. Rather, the endothelium also has the receptors to bind these cytokines. And once the endothelium receptors bind the cytokine, they retract. They have endothelial retraction to give us spaces through which the macrophages will leak out through the interendothelial gaps, and they will come out and they will differentiate. Okay, this is the first form of the macrophages. They originate from bone marrow, and these are activated macrophages. What about the resident sentinel macrophages? Where do they come from? These microglia, these alveolar macrophages, Kupffer cells, and the sinusocytes. Where do they come from? They come from the embryonic yolk sac. They come from the embryonic yolk sac. Okay, from the embryonic yolk sac. These embryonic yolk sac cells and the feeder and the fetal liver, they are the source from which we will have our resident tissue macrophages, known as 1. Kupffer cells, 2. Sinusocytes, 3. Alveolar macrophages, and 4. Microglia. Okay, now this is the origin. We finished talking about the origin. Let us now talk about how does the macrophage know what to do. Should the macrophage promote inflammation by beginning the process of recruiting more macrophages and engulfing this necrotic debris and engulfing the invaders and destroying the tissue, or whether they should stop and have anti-inflammatory and pro-healing actions? So the macrophage can do both. It can have pro-inflammatory actions, microbicidal actions, and it could also have pro-healing and anti-inflammatory actions. So how does it know? So we have two paths, and you need to know them. The first path is called the classically activated macrophage M1. So in the classically activated macrophage M1, what happens is we have once the monocyte, this is the monocyte, this is the shared monocyte. Once the monocytes receptors detect microbial products like these lipopolysaccharides, glycoproteins found on the surface of these invading microbes, these bacteria, these viruses, the bacteria, the viruses, the fungi, the parasites, or once they bind the toxin of these bacteria, or once we have toll-like receptor ligands or interferon gamma. Once these ligands bind a monocyte, the monocyte will immediately perform pro-inflammatory actions. And this is called the classically activated macrophage, the M1 pathway. In the classically activated macrophage, we will have the release of, we will have two things, 1 and 2. The first thing, we will have release of reactive oxidative species and nitric oxide and lysosomal enzymes, and that will give us microbicidal actions, destructive and phagocytosis, and the killing of bacteria and fungi. And number 2, we would have a release of interleukin 1, interleukin 12, interleukin 6, and chemokines to further promote, you see the positive sign, to further promote inflammation, to recruit more and more macrophages. So the classically activated macrophage pathway, pathway 1, M1, that promotes, leads to positive inflammation, promotes more inflammation. And this is called the classically activated, this is very important. The classically activated macrophage happens when the monocyte detects microbial products or toxins or toll-like receptor ligands or interferon gammas or cytokines that indicate there is an ongoing attack or stressful stimuli. And then the classically activated macrophage M1 pathway will be initiated. We will have the release. This macrophage itself will release interleukin 1, interleukin 12, interleukin 6, and chemokines to recruit more and more macrophages. And it will start fighting by releasing reactive oxidative species and nitric oxide by engulfing these products, and while it engulfs them, there are intercellular, you see they have intercellular lysosomal vesicles, and the lysosomal vesicles will bind the phagocytic vesicle. You know, the phagocytic vesicle engulfs the necrotic debris and engulfs the microbes that have been swallowed by the macrophage. Once inside, there are lysosomal vesicles that will fuse with these phagocytic vesicles, and now we will have a phagolysosome, and then it will destroying intercellularly, get rid of them properly. So this is the first pathway. Which pathway is pro-inflammatory? It is the classically activated pathway. However, once the fight is over and the macrophage destroyed potentially most or all of the necrotic debris, all the necrotic tissue, and all of the invading microbes, now a different series of cytokines will be released by the macrophage. And these cytokines will be interleukin 13 and interleukin 4. Once monocytes in the blood detect interleukin 13 and interleukin 4, they will no longer perform pro-inflammatory activity. They will no longer release interleukin 1, interleukin 12, interleukin 6, and chemokines or reactive oxidative species. The battle, the microbicidal action is done, is finished. Now the monocyte will be activated by a pathway called the alternatively activated macrophage pathway, M2. M2 is the alternatively activated pathway. What does the alternatively activated pathway do? The alternatively activated pathway would secrete interleukin 12 and TGF beta, and these growth factors and these cytokines will inhibit inflammation, and they will begin the healing process, anti-inflammatory effects, wound repair, and fibrosis. So it's very important for you to understand that we have a monocyte that could potentially differentiate into either of the two pathways, depending on what cytokines are released. And what cytokines are released depends on what is the stage of our inflammation. Do we have an ongoing combat, and do we need more macrophages to come engulf and swallow and phagocytose all of the necrotic debris and all of these invading macrophages? Then interferon gamma, TLR, lesions, and toxins and microbial agents will be there, and they will be detected by the monocyte, and then the monocyte will differentiate through the classically activated macrophage, M1 pathway, and we will have this pro-inflammatory activity. But if the fight is over and the combat is over, then the macrophages there will send interleukin 13 and interleukin 4, and that will cause circulatory monocytes to differentiate through the alternatively activated macrophage M2 pathway, and that will give us the process of healing. So just to recap real quick, we have to understand very well that if we had a normal healthy tissue, this normal healthy tissue is susceptible to ultraviolet radiation, susceptible to chemical agents like corrosive chemical detergents and agents that are harmful. The tissue is susceptible to physical agents like very high temperatures or very low temperatures. There's also microbial agents like the bacteria, the fungi, the viruses, and the parasites. And the trauma, the tissue is also susceptible to trauma, vulnerable to trauma, like contusions and bruises and so on. And the tissue would normally, all these cells will try to fight back and overcome that stressful stimuli. But if the stressful stimuli, the harmful agents, their intensity is severe and their duration is very long, what would happen is the cell will now become injured. We will have cell injury. Cell injury could be reversible cell injury or irreversible cell injury. If we have a reversible cell injury, the cell will go back to being a normal cell. We would have normal tissue back again, resolution. But if the cell injury is irreversible, we would now move on to a cell death. And if the cell death takes place through apoptosis, that means the cell had enough time to realize that it's damaged and it needs to get rid of itself through programmed cell death and not cause, you know, all of the intercellular substance to leak, spill out, and these lysosomal enzymes destroy nearby tissue cells. But if it's the inflammation is so, but if the agents, the stressful agents are so severe and so intense, we would now have irreversible cell injury that leads to cell death, not by apoptosis, but rather by necrosis, and that leads to the process of acute inflammation. And acute inflammation, resident sentinel cells, they detect that necrotic debris and those, microbes, and the resident macrophages. We said they originate from the embryonic yolk sac and the liver in the embryological development, and they send cytokines that cause the recruitment of circulatory monocytes, and to cause these monocytes to start gravitating and migrating to the site of tissue damage. And we also said the cytokines don't only bind to the monocytes, the inflammatory cytokines also bind to endothelium and cause endothelial retraction. Endothelial retraction causes for us interendothelial gaps, and these interendothelial gaps are wide enough for the monocytes to leak out and transmigrate from the blood circulation into the tissue. And then these macrophages, they have their own metalloproteases where they degrade the extracellular matrix in order to pave the path for themselves to arrive at the site of inflammation. And these monocytes that are circulating in the blood, they arrive there because they did not come from the embryonic yolk sac and the liver, but rather these monocytes, these circulatory blood monocytes, they came from progenitor stem cells, hematopoietic stem cells that originate from the bone marrow. And once the macrophages arrive there, they start secreting more cytokines to bring in more monocytes. And once all of these macrophages arrive there, they start degrading and engulfing and phagocytosing all of the necrotic debris and all of these these invaders, these microbes, and perform microbicidal activity and pro-inflammatory actions. However, once the inflammation has ended, what happens is now new different cytokines, pro-inflammatory activity of the macrophages is initiated by the classically activated macrophage, which is caused by the release of interferon gamma and other microbicidal promoting cytokines. When the fight is over and inflammation is done, hopefully, and full elimination of necrotic debris and full elimination of invading microbes is finished, then new and different cytokines that would lead to the activation of the alternative macrophage pathway, that is M2, and these cytokines are interleukin 13 and interleukin 4, and then we would have the secretion of interleukin 10 and tumor growth factor beta, TGF beta, and that leads to inhibition. You see the minus sign? Break. To stop the inflammation, have anti-inflammatory and pro-healing actions, and we would have anti-inflammatory effects, wound repair, and fibrosis. So I'm just gonna bring you to visualize to visualize the diagram closer, and okay, see the bone marrow, hematic blood monocytes. Okay, thank you very much for your listening, and see you in our next discussion.